Hello, everyone. I'm Aseel Salameh, a U.S. master's student. I'm here to represent on integrating bond slip models into finite element modeling of Cfrp strengthened concrete prisms. This research is a part of an ongoing effort to enhance the accuracy and reliability of structural analysis of Cfrp strengthened concrete structures. Let's start with an overview. FRPs or fiber reinforced polymers have become increasingly popular in modern construction, particularly in critical infrastructures like bridges, high-rise buildings, and marine structures. Their use include repairing, strengthening, and reinforcing. In the context of structural strengthening, FRPs are an ideal choice due to several key factors. One, they offer a significant weight reduction compared to traditional steel reinforcement, which is crucial in application where minimizing added load is essential. Two, their resistance to corrosion and chemical attack makes them particularly suitable for environments where steel will typically degrade, like coastal or industrial areas. Three, their flexibility in terms of shape and size allows for tailored solutions to specific structural problems, and hence shorter installation times. As shown in this slide, FRPs can be applied in various forms. One, externally bonded reinforcement systems, EBR, or near surface mounted systems, strips or rods. EBR involves bonding FRP sheets or plates to the exterior of the structure, while NSM involves embedding FRP strips or rods into grooves previously cut into the concrete surface. Each method has its advantage. For EPR, it's easier to apply, but more susceptible to environmental exposure, while NSM provide better protection to the FRP material, but require more invasive installation. One of the most critical challenges associated with FRP strengthened members is the potential for failure modes. We have two main failure modes, delamination and debonding. Debonding occurs when the FRP detaches from the concrete surface, which can significantly compromise the load-bearing capacity of the structure. This type of failure is often sudden and can lead to complete loss of the strengthening effect, making it one of the most feared scenarios in FRP application. Delamination is a form of debonding, as shown in the second photo, that occurs by concrete cover. We can understand that the interface between concrete and FRP sheet determines the effectiveness of that load transfer and the overall structural integrity, because it's the main reason for debonding or the failure mode. And this brings us to the concept of bond slip model, which are vital for accuracy predicting of the performance of FRP members. Bond slip models describes the interface behavior between the FRP and concrete, capturing how stress and strain are transferred under loading conditions. The relationship between bond stress and slip is nonlinear. As shown, we have many models studied in the literature: cut-off, elastic plastic, bilinear, Popovic, all different models, but they are all confirmed the increasing part at the beginning and then decreasing part of the bond slip behavior. The significance of this research lies in its ability to enhance predictive accuracy in finite element modeling simulations. By incorporating experimentally validated bond slip models, we can improve the structural performance predictions of FRP strengthened beams. And this is not only leads to more reliable designs, but also provides engineers with better understanding of load transfer mechanisms between FRP and concrete. Additionally, this research provides a robust foundation for developing advanced design guidelines and standards, which are essential for the safe and effective implementations of FRP technologies in construction. To get our calculated bond slip model, an experimental program using 3 specimens, each of a cross-section 100 by 100 millimeters, and the length of 500 millimeters. The specimens were strengthened using CFRP sheets. applied through a wet layup procedure. The wet layup process involves manually preparing the specimen surface and then applying the resin and placing the FRP material onto the surface, ensuring that it adheres properly and cures to form a strong bond. Then the specimens were tested under a 3-point bending test setup, as shown, 2 supports and point load in the middle. During the test, the constant loading rate was applied until failure. Before testing, 7 strain gauges were attached to the edge to the FRP sheet to monitor the deformation and record the strains. For calculations, we assumed linear elastic behavior for materials and used equilibrium and compatibility equations to obtain values for slip and bond shear stresses. For each segment between 2 strain gauges, I and I+1, the stresses and the slip are calculated and then plotted for all segments, so we get our bond slip model. From our bond slip model, we have 3 parameters, important parameters that we need to imply them in finite element model. Tau max, which is the maximum stress for the beam, and the corresponding slip for tau max and the maximum slip. Our bond, then to verify accuracy for our calculated bond slip models, we calculate these parameters, the main parameters, the 3 parameters from 3 models, famous models in the literature: Kappa 2001, Broson's 2001, Fricketti 2007, and Liu. We got a good agreement for this, and then now let's move to finite element modeling methodology. We developed a 3D finite element model using ANSYS 19. The geometry of the model was designed to replicate experimental setup as closely as possible, including boundary condition and loading scenarios. By using this model, we were able to reduce the computational efforts by modeling only a quarter of the beam using symmetry. And for modeling concrete elements, the component of solid 65 have been defined, and this component is able to crack and crash. And for FRP and epoxy, solid 185 have been defined. For material definitions, the same for experimental program, concrete of strength 60 megapascal has been designed, defined, and for Cfrp sheet, the values reported by manufacturer for 2000 megapascal as a modulus of elasticity, 4900 megapascal as tensile strength. And to define the interaction between the Cfrp and concrete, as previously mentioned, we defined the main parameters of bond slip model, calculated from experimental data, tau max, for the 3 specimens average of 4.676 defined, and the corresponding slip for tau is 0.2487 millimeter, and the maximum slip 0.6486 millimeters. To verify our model, we compare the predicted ultimate load capacity and failure modes with experimental data. The validation showed a good agreement with finite element model, successfully capturing the typical failure mode of the strengthened specimen, which was debonding at FRP concrete interface as shown in the experimentally and in the model as shown in the slide. And for ultimate load predicted by the model was 16.9 kilonewton, and while experimentally it's 15.13 kilonewton. In conclusion, the integration of experimental point-slip models into finite element modeling has proven essential for accurately capturing the interface behavior between Cfrp and Concrete. This approach not only improves the prediction T-bonding failure, but also provides a validated tool that can be used for a design and analysis of Cfrp strength and structures. By enhancing the accuracy of these models, we can contribute to a safer and more efficient construction practices, particularly in the retrofitting and strengthening of existing structures. Thank you for listening, and I'm happy to answer any question you may have.